All right, this lecture is on parallel circuits. It says, be miserable or motivate yourself. Whatever has to be done, it is always your choice. Parallel circuits are all about choice. So you either do it or you don't, and you'll see what we talk about in just a second. So you should be able to calculate the total resistance for any object in parallel, and you should be able to calculate the total power, voltage, or current in a parallel circuit. So remember, we talked about parallel as the charge has a choice as to what path it moves down. So this positive charge, when it gets here, it can actually go this way, or this way to get to the other end of the battery. So when you remove a resistor, it doesn't stop the others from functioning. So if I were to cross this resistor out all of a sudden, there's still two pathways for this charge to get to the other end of the battery. So it's still going to function whenever it does that. A great example of something wired in parallel would be this surge protector. All of these can be plug-in resistors, and you still have an alternative pathway. If you don't have something plugged in here, there's still a pathway for this to get to the other end of the voltage source. Now, electrons don't actually contemplate where they're going to go. They follow the path of least resistance. So let's say that this has a very, very high resistance value, then most of the charge is going to go here. Not all of it, because if I get a lot of charge here, it backs up, and then now I've got a lot of an easier path to go here. So don't think of it as really a choice. It just goes to the path of least resistance. There's more, there's different options for reducing the charge. Resistors in parallel. If one goes out, the others remain on, and you can see that right here. These are all wired in parallel. So if this is unscrewed, these two are still on because there's an alternative pathway for them to go. Now, applications of parallel wiring, we've talked about the outlets in your house. If the fan is on, not all the other electrical devices are on. You can have the fan on with the light off. They're wired in parallel. Resistance always goes down when you add resistors in parallel. Now, how you actually calculate the total resistance in parallel is you add the inverse of the objects. So, for example, if I was trying to find the resistance in parallel and I had two 5-ohm resistors, it'd be 1 over 5 plus 1 over 5. It'd be 2 over 5. But then you flip it. That's the keys. You have to flip it. And you'll see this as an example. There are multiple examples that we're going to do as you work through the module. But the key thing is you add the inverses and then you flip them. Now, one of the great things about parallels is the voltage is always the same. All wires that are in parallel have the same voltage in each branch, regardless of what they are. They all have the same voltage. So every time you plug something into a surge protector, you get 120 volts no matter what. It is the same in all branches, no matter what path there is. As long as it's in parallel, they have the same voltage. The current, however, is different. The current is different because you're providing alternative pathways for charge to go in different branches. Now, conservation of charge still occurs, so if you have 12 amps going into where it splits into parallel, you're going to have 12 amps when you come out of there, but you can have 4 in one and 6 in one and 2 in the other depending on the resistance. So the total current has to be the same, but the individual branches can each have different amounts depending on the resistor values. And how you can figure out what it is once again you have the voltage drop is equal to the current in that branch times the resistance in that branch. And like I said, you're going to see a lot of examples of this. The trick to all these series and parallel problems is all in the problems that you work out through the module.